So today I'm going to talk about this recent paper by me and friends on gravitational wave discovery space of pulsar-timing arrays. As I think you all know, in the last few years there's been a real buildup of interest in employing collections of very stable millisecond pulsars as gravitational wave detectors for low frequency gravitational waves. Where by low frequency I mean 1 over a few years or a year, something like that, 10 to the minus 8 hertz. The idea is that as these gravity waves bathe the Earth, they will cause timing residuals, extra timing residuals in the arrival times of pulses from these pulsars. And these timing residuals will be correlated on the sky based on the location of the source or isotropic. And so they have a definite pattern, and if the measured pattern of residuals is large enough that it could not have arisen out just out of coincidence, then you say you've made a detection of gravitational wave. That's after you've checked, of course, that there aren't any more prosaic explanations like a bug in the tempo tube that many of the observers are using. So the bread and butter source for pulsar timing arrays is expected to be, drum roll please, black hole binaries. I know you would never have guessed that. So it's the black hole binaries, but for these would be sort of very massive black hole binaries, like 10 to the 8th or 10 to the 9th solar masses. But in this talk, I'm going to discuss not the bread and butter source. We're going to step back a bit and ask ourselves, what are the possible constraints on just about any source that could be out there, right? For this fairly new sort of gravitational wave detector. Oh, and this is an artist's conception of a pulsar timing array with lots of pulsars in the Earth that many people are already. Okay, I'm going to give, so I know that when I listen to talks, it helps me get in the mood to know the author's motivation and sort of a little bit how he worked. So I'm assuming some of you are like that too, so I'll talk about a little bit of motivation. So at JPL, we have the Deep Space Network, which is our main way of communicating with all the unmanned satellites in the solar system. And that includes 3 very large radio dishes, about 70 meters. Let's see, there's one in California, there's one in Spain, there's one in Australia, and Canada. And these are substantial radio telescopes, 70 meters, about the same size as parks. While these are mostly busy communicating with satellites, they do have dead time when there's nothing to do. Each of them usually has something like an hour a day when there's nothing. Free, and so we've been thinking, we have a group of us here at JPL, well, what can we do with an hour per day? Can we use them sort of to time pulsars for pulsar timing arrays? In fact, and one of our co-authors, Waleed Majid, has been building a state-of-the-art back end for the DSM. And then we have sort of weekly group meetings, and for a while we were kicking around, what will we do with it, with 1 hour a day? And one of the thoughts was, well, typically in most of these collaborations look at each pulsar every 2 or 3 weeks. What if we looked at something every day, for example? That would, if there's any source out there, say with frequencies of say 2 days, with periods of 2 days, maybe we would see them and nobody else would. So I then did some back-of-the-envelope calculations for supermassive black hole binaries, and I realized that it was very unlikely there would be any supermassive black hole binaries with periods of like 2 days. However, then I started thinking a little bit more generally. Said, well, the sources that we talk about for PTAs, for pulsar timing arrays, are almost the same ones we've talked about for LISA and LIGO. They're ordinary black holes, cosmic strings, and stochastic backgrounds from supermassive black holes or from cosmic strings, or maybe some other stochastic background from the early universe. But this is this whole new technology in this other waveband. Maybe would it be worthwhile thinking if there could be something else out there that we want to look for, and partly the idea to broaden that we wouldn't want to have a search strategy that precludes us from seeing it. For example, if there were I don't think there are supermassive black holes out there, probably with periods of 2 days, but maybe there's something else. And then it would be a very bad idea to just check them every 2 or 3 weeks, for example. So we wanted to think of these things more generally. And part of my inspiration, and my tip is here for this, was actually just like one sentence I read once. So I knew that Zimmerman and Thorne had written a paper called "The Gravitational Waves That Bathe the Earth, Upper Limits Based on Theorists' Cherished Beliefs." And I remember, I think it was in your unpublished textbook probably, there's a short description of that they basically used energy arguments and statistical arguments to arrive at some limits, and that's all I knew. So I said, okay, well, I can do the same. And I was always intending to read it, but in fact, I didn't even get around to reading it until it was just about done. And I was referring to in the paper as this classic work, and Michaela always laughed at me because said, "You haven't even read it yet." And unfortunately, I did read it before we published it. And I was always reading, oh my God, I hope there's not everything in here is in Kip's paper. And some of it was, and I don't credit you. But fortunately, there's some things that weren't. So for Kip was very interested in the LIGO context. So 100 hertz. This is a different context. Kip's paper, they basically restrict themselves to Z less than a few. And I find a lot of interesting stuff conceivably at very high Z. So it's good to sort of read things myself. And now I'm going to outline the rest of the talk. I'm going to, maybe a third of the talk is just a review of pulsar-timing arrays, some of the physics, some of the astronomy, a little of the history. I've just actually been learning the history in the last day or two to give this talk. Another good reason to give talk. I'm going to talk about constraints on measurements of what I'll call the direct part of gravitational waves, which is just to distinguish it from the memory part of gravitational waves. So I get rather different results for both. For both, I'm going to discuss the low Z case. We're in here for this talk. When I say low Z, I really mean Z less than a few. And in the high Z case, where I'm going to mean Z up to like 10 to the 10th or 10 to the 20th or something like that. And then I'll quickly do summary conclusions. Let me just briefly review a little of the early history, the early papers. So this idea of using a collection of pulsars to measure gravitational waves goes back to, you know how to pronounce his name, Kip?
CaJAGWR.
CaJAGWR, thank you.
He was a member of Zeldovich's research group, Zeldovich and Grishchuk
Okay.
in Moscow.
Thank you very much. CaJAGWR wrote a paper in '78, I just wrote it yesterday, which he looks at several ways you might be able to measure gravitational waves with pulsars. I don't know if it's independent or not. Detweiler, I should check that, in '79 wrote a very nice paper on using using pulsars to measure gravitational waves.
I think it was independent.
It probably was, yeah. Another interesting thing is that an even earlier paper by Estabrook and Wahlquist has all the same mathematics in it, and is beautifully written a few years earlier. They were interested in Doppler tracking. So here's the Earth, and there's a spacecraft, and you have radio waves going back and forth between the spacecraft and the Earth, and they're have their frequency shifted by the gravitational waves. But if you replace the spacecraft by a neutron star, it's absolutely the same, right? In fact, this is roughly speaking, from Estabrook and Wahlquist. So from '75, they know that if you want to look at the change in frequency at the Earth, that you measure the gravitational wave. It's a sum of two pieces. It's a piece that's due to the gravitational wave strain at the Earth at that moment. The gravitational wave strain at the pulsar, say, before, when the pulse was sent. Both of those dotted twice into the vector connecting them, and then there's this extra factor 1 minus n dot k, where k is the direction of the gravitational wave. It's a famous result, and if you haven't read the paper, I would recommend it. So that's this formula is the essence of, it's the basic formula for the basic physics of the process. And an important point is that the delta nu over nu just depends on the h of the Earth and h of the space at the pulsar. However, for almost any source, for all the different sources on the sky, the Earth, of course, is feeling the same gravitational waves, which will lead to a correlated pattern, while an equal contribution will be coming from the gravitational waves passing over all the pulsars, but they won't have any obvious correlation at all. So it's the Earth, the part about the waves passing over the Earth that's really most measurable. Okay. And I'll mention a little bit later, in more detail, another important paper, an early paper. All these were very prescient because there wasn't a huge buildup of interest in this until in the 2005 or so. So these were amazing, 25, 30 years prescient. Hellings and Downs that made that point exactly. That for any given pulsar, the timing residuals caused by gravitational waves could just be timing noise, right? So what you really want is a collection of pulsars, and so then you can look for correlated timing residuals, and they form, in fact, a pattern on the sky that's very recognized.
So the gravitational waves at the pulsars are a form of noise that makes it harder to detect.
Yes, that's true. So if you have, like, say, of course, 40 pulsars, it goes into 1 over square root of 40. Not the biggest problem. Okay. Now let me just do a back of the envelope estimate of strength of what you need for detection and source strength, just to get us started. So what's the size of the timing residuals? Well, typical timing residuals for a pulsar are of order h, where h is the square root of h plus squared plus h cross squared, divided by f, because that tells you it builds up over the length over a period, where the factor 120 is in front. That includes partly angles and partly the fact that f is gone up and down during one whole cycle. And if you look at the signal to noise square from a bunch of pulsars, so for any one pulsar at any one instant, it's just, of course, the size of the timing residual from the gravity wave divided by the RMS noise in the pulsar. Part of that is noises from electronics, and partly intrinsic to the pulsar. And then it goes up like the square root of the number of observations, which is the number of pulsars times the number of observations per pulsar. And here, just to be simple, I'm assuming that delta T RMS is basically the same for all the pulsars, just to simplify the formula. Okay. Now, if you plug in fiducial numbers, say the typical timing, say that in a 25-minute observation, you can measure the arrival times of a pulsar to say 0.1 microseconds, which you can do roughly for the very best, most stable pulsar. Let's say we're looking for gravity waves at f equals 10 to the minus 8 hertz. It's 1 over 3 years, basically. Let's say, be optimistic, say we have 40 well-timed pulsars. That's more than we have now, but the number keeps growing. And let's say you have 500 observations per pulsar. Let's say 1 a week for 10 years. And then they say you want signal to noise of 7, and you just plug that in here. You need a strain of something like 10 to the minus 15. Was that at all, a reasonable strain? Well, if you take, for example, one example of a very, very massive, supermassive black hole binary, 2 10 to the 9th solar mass black holes, when they're pretty far away, when their frequency is 10 to the minus 8 hertz, they still have a lifetime of about 50,000 years, right? So the density is fairly, it's not so small, right? So it's not an unreasonable estimate to say the nearest one might be around 300 megaparsecs away. And then you go back to the previous page, and or just look at any standard book, and you use the masses and the frequency and the distance, you get to the h is around 10 to the minus 15, which is why people are excited about this subject.
Curt, can I follow up on something you just said a minute
Sure.
ago? That the intrinsic timing errors, some of it is from the pulsar, and some of it is from the electronics of your receiver.
Yes.
And of course, it's the same receiver, maybe, looking at multiple different pulsars, but at different times. Is there any chance that that would introduce some correlations in the timing?
I mean, there's certainly the thought is that most of the stuff in the receiver is thermal, and so it's
random.
white. It's white, and so it's oh, and you're only looking at one pulsar at a time.
At a time, you're not looking at more than one pulsar at a time. So you
I
expect
don't-
no correlation between the timing noise from observing pulsar A and the timing noise.
So the atomic clock, of course, is common to everything on the Earth. So clock noise appears as a monopole signal, but it's a monopole.
Right, that's true. So that probably no.
Okay, I just wanted to.
Yeah.
GPS position errors have been another.
There are a lot of things you might worry about, right? I don't think
Changes
it's,
in the electrons, putting more cable in the computer telescope is a lot of nanoseconds.
Is it true that noise in the detectors is comparable to the intrinsic timing noise at the pulsar? I guess
It's of a different spectral shape. We think that we see that the noise intrinsic to the pulsar is actually very low frequency. It's low frequency stochastic noise, like a random walk in the pulse frequency, for instance. And that's completely different from the receiver noise.
and this is this slide is just to show this curve. So Ron Helling's now worked out that if you have isotropic distribution of sources on the sky, then you do get correlations in the timing residuals from pulsars based on their angular difference, and that follows this famous Helling's-Downs curve. All right. So if you're looking for a stochastic background, and you find timing residuals, and a test, or what you're looking for is correlations that have this angular dependence. This slide is just to make the point that we're interested only in the very most stable rotators. So not that many pulsars have timing noise below 0.1 microseconds. And so of all the pulsars out there, we're not interested in the vanilla ones. We're interested in the millisecond pulsars that are old and the best of them. This is stuff I only learned in the last day or two. So, I'll talk about myself. So, some people are really good, I've noticed, at saying, exactly when they did things, I remember things. Like, I remember I was talking to so-and-so at that conference in Madrid in July of 1918 or 1981 or something. And I remember, it was about 3 decades ago. Anyway, I was trying to remember. I remember distinctly, suddenly, in my gravitational wave world, people were talking about pulsar-timing rays. And I did the dutiful thing, and I went to my piece of paper, and I worked out lots of back-of-the-envelope estimates so that I had some idea what the field was like. I couldn't even remember what year that was. I think it was a while ago. So I went on to ADS 2 days ago and just looked at citations to that water. This is one of the original papers. And you can see this growth from 1979, and you can see a big ramp up in around between 2003 and 2008. Looking at citations of these papers that cite it, I noticed that it was clear that a very important paper was this paper by Genet, which basically was very galvanizing, and which did in fact was the impetus for starting a number of collaborations, pulsar timing array collaborations, that started to try to really seriously beat down the noise and to look at lots of pulsars. And he laid out first a vision, that we can achieve this in a certain number of years. And he wrote down all the basic formulae and basically gave a game plan. I talked to Joe Lazio about this, and I asked if he thought that was very important. And he suggested he thought it was probably the reason for the paper was that was more discovery and instrumental changes. He said around that time he guessed there was a big ramp up in the discovery of millisecond pulsars. It's kind of true, yeah. There was little kind of changes around 2005. Nothing happens right there. And then I couldn't find one. If I looked at a plot that showed the quality of electronics, that would probably also be improving around that time.
The first millisecond pulsar was discovered in 1982, I think, which explains the first peak. That was a discovery of the millisecond pulsar, which we practically.
Thank you very much.
Another important year, maybe 2003, where Dick Manchester, the big boss of the Australian PTA, actually got his grant, the ARC grant in 2003, which the quantum community knew. So they knew they were going to develop the instruments and all that.
Wow. Okay.
I should also explain my personal feelings, though. In 1990 and 2000, I gave presentations to the decadal survey saying that pulsar timing was the best way to discover gravitational waves and could beat LIGO if only they put in 1% of the money that was going into LIGO. And notice that both of those were precisely minimum and had no effect.
Oh, I would say you were very prescient. You were a voice in the desert.
Well, prescient, but it wasn't a desert. So.
Okay. Well, that was a little bit of sociology history. 3 collaborations were formed: European timing array, nanograv, one other. Sparks. Thank you very much. And now they've all joined together to form the International Pulsar Timing Array, encompassing all 9 or so radio telescopes across the planet. They're looking at about 37 pulsars that monitor regularly. I'll show you the list. And just by way of, this is a word on nomenclature, because it's confusing. Different people use this word differently. For some people, the array is obviously the array of pulsars. For some people, it's obviously the collaboration. For some people, it's obviously all the detectors. And so you have to determine context. This is the list of all the pulsars currently being monitored. The thing I would really call attention to is there are 40 of them, but the more important is that if you look at the residuals in the measurements, a lot of them are at the sort of, in terms of microseconds, kind of at the 0.1 level. There's 0.21, 0.11, 0.15.
First one is 0.03.
Oh yeah, even 1 is even better, yeah. So that is not an unreasonable level to aspire to for some large number of pulsars. And if you look at the current state of the art, first there are 2 points to this plot. One is to show you again just the band of pulsar timing arrays compared to the band of mission formerly existing as LISA and LIGO. So not the 100 hertz band for LIGO, and minus 3 hertz for LISA-like missions, and down to around 10 minus 8 hertz for pulsar timing arrays. And the current bounds from, say, nanograv are H's stochastic background of H corresponding to a little less than 10 to the minus 14, and they expect to be moving down around 10 to the minus 15. Okay? And these are the expected ranges of sources. And the current limit is H must be less than 7 times 10 to the minus 15 at over a year.
So there are 2 bands there. There's the massive black hole band, which you could sort of make some guesses at, and then there's the strings.
Yeah, so I don't know what, that is too narrow a band for the strings.
How can you even make a band with the strings?
So this would be a stochastic background for the strings, presumably. And so I didn't grab this slide, I didn't actually look at it carefully. But if you look at the stochastic background from cosmic strings, it does tend to be fairly flat over a fairly large region, and it does tend to just depend on a few parameters.
And those parameters are completely unconstrained and unknown.
Right, I'm agreeing with
Not
you.
bigger than it should there.
Yeah, I'm agreeing with you.
They're now constrained, but they could extend out to minus.
They could.
I'm sure that is true. It could be way down there.
I mean, they may not be cosmic strings. I mean, in fact, people really.
Right.
So
I agree with you. If you weren't a sophisticated audience, maybe I would have shown that.
Curt, does the dip at around 1 per 20 years mean this is 20 years of observations?
Let's see, this looks like it's 1 over a year.
No, I'm looking at the dip,
Where are you
the
looking?
minimum,
That?
yeah.
Oh, yeah, absolutely. Yes.
Curt,
In 2020, it will be 20 years.
It's 1 over the observation, roughly, or half the observation.
Curt, I'm curious about what that spike is.
I assume that's 1 over a year.
Right.
Yeah. The reason being that,
there's lots of things that models are done per year.
yeah,
The position of the pulsar comes from timing, and because we don't know the position of the pulsar, except from timing, you fit for something.
yeah, it would be very unlucky to have a gravitational wave that was from a distant galaxy. That was
There's a
exactly
little blip at 2 per year, which is the eccentricity of the orbit. 6 points.
That's right. Thank you for asking. In fact, this relates to what you just asked. So this is a bit of a digression, this slide, but it's an important check, I think. So recall at the beginning of it, we were saying, could there be sources at, say, 10 to the minus 5 hertz? And an important check we wanted to do, this is from one of our collaborators, Sarah Birch-Spolauer, was, okay, well, if we actually, the word gravitational wave at 10 to the minus 5 hertz might tend to actually fit it out. We didn't think so, but we didn't know. So she did actually go to the trouble of taking one particular pulsar, J0613, which as I recall is like a 3 millisecond pulsar with like a 1.2 day orbital period, adding a gravitational wave and giving it to tempo and saying, give me the parameters, and seeing how much of the signal was absorbed by the misfit in the parameters, or this shows how much is capped. So the dips show where you lose signal, right? So basically, above 10 to the minus 7 hertz, you have almost a complete signal. It's capped, except for very, very narrow bands. And those narrow bands are places like 1 over a day, or sidereally. Since she was doing them every 2 days for the observations, and this was for 1,000 days of observations, you get harmonics of that. You get harmonics of the orbital period, things like that. So except for a few very clear places, the band is relatively free, which is to say, yes, if there were a randomly placed source, one of these frequencies, it would not be fit out by the timing programs we already have. So it was a check.
Well, what's happening at the left?
What's happening at the left side, well, it's like, so this is clearly about 1 over a year, right? 1 over a year.
Well, so
I
if you
think
look at
twice
the full
over a
fit,
year.
if you look at the full fit.
So it's clearly going bad.
Yeah.
Above, so above 10 to the minus 7.5. Oh, let's see, so you're saying,
I think that's probably because you had 3 years of observation or something.
yeah, that's
So
right,
you
that's
get-
right,
You start losing period.
that's right.
Well,
That must
but then
be-
how do I
So 10
judge
years,
that?
so probably, I think Sterling is completely right. So for 10 years, or 20 years, it probably comes back up and moves to the other side, except for maybe narrower dips.
And is that why nanograv had limits at 10 to the minus 9 hertz? Even though this suggests that.
Well, I've been doing it for more than
Yeah,
There are a couple of pulsars for which there's 20 years of data that's not very good, and there are others for which there's 10 years of good data, and others for which there's 1 year. So
Well, I'm wondering whether, for
We should
example.
redo this, I guess, for a longer data set, I think is what.
Well, I'm wondering whether they, you know, the obvious simple thing to do is to run tempo on a pulsar by pulsar basis,
Mhm.
get the residuals, and then do your analysis on the residuals. But to avoid tempo taking it out, could you do a full fit with, you know, for all the pulsars at the same time with tempo?
Yes, you could in principle certainly do that. And
that's
that's
what
what,
you already love a student who's pioneers.
yeah, it wouldn't be a killer, so I don't think, if for that reason, you're right, there, even if there were fitting things out, they would, you probably wouldn't fit out the same way for all different pulsars, so they're still low. So, and there might, and then you could, you know, make a larger model. So this was, we didn't investigate that because we were mostly interested when we did this in the higher frequencies, and mostly the basic take-home point was not a problem anyway. That was, I'm glad we were motivation early, that's why we stopped. This is useful background for the next slide. So we already have a number of limits on omega gravity wave. There's one limit from Big Bang nuclear synthesis that all the gravity waves in the universe before Big Bang nuclear synthesis, you look at the ones that were there at the time of Big Bang nuclear synthesis, which was the around 10 to the 10th, you look at their energy density now, it has to be less than around 1.5 times 10 to the minus 5. Does everybody here know where that comes from, or should I say that in 2 minutes? 1 minute. Everyone who doesn't know where that comes from.
Where the limit comes.
Yeah, but you understand it. No one's answered either way, so let's say it fast. You all know that, I think from Big Bang nuclear synthesis, there can't be 4 species of neutrinos, and the answer and the reason is, if there was a 4th species of neutrino, then when the universe reached the temperature at which Big Bang nuclear synthesis occurs, it would have more energy density than if there are only 3 species. So the universe would expand through that faster, cool faster. The neutrons would have a harder time as they were starting to decay away, finding protons to grab onto to form helium, and the helium abundance would go down. So just as you can't have too much energy density in neutrinos, you can't have very much in gravitational waves, or you'd have produced less helium. Okay?
Is it also true that the scattering would break up the newly formed nuclei?
Scattering of what?
Neutrinos or gravitational waves?
I very much doubt that.
So I think they're just energy at that point, not interacting.
The neutrino scattering cuts out at about 1 second.
Thank you, that's the right answer.
So there's negligible scattering.
So this happens, of course, in 3 minutes.
Nucleus
About
is
3
3
minutes.
minutes.
3 minutes, the first 3 minutes, right?
That's
You need to
good.
take money.
Okay. Probably the best constraint though in a narrow frequency band is, and this is the most recent one, is omega gravity wave less than around 10 to the minus 9 at 3 times 10 to the minus 9 hertz from pulsar-timing. The current constraint from LIGO is around, again, in LIGO's frequency band around 100 hertz, around 7 times 10 to the minus 6. You'll find it better than that. And there's also, again, a neutrino, there's also a bound from large-scale structure. This bound is a great bound, except it only applies to gravity waves that were produced before z of 10 to the 10, before the first 3 minutes. And we're like to some constraint on gravity waves that might have produced at z equals 100, say. And the claim is that omega gravity wave from large-scale structure can't be bigger than 6 times 10 to the minus 3. Again, this is just changing and taking a neutrino bound and plugging in gravity waves instead. You have, it's hot dark matter. Gravity waves would be hot dark matter, and they would form less clustering. So the claim is that the current limit on clustering can be used to constrain this, just as it can be used to constrain hot dark matter. So I'll be using this frequently. Okay, finally I'm getting to the main point of the talk, which is the constraints on discovery space. I'm going to divide first into talking about direct radiation. I'm going to start first at z less than a few. And I'm going to make a few assumptions. We know that omega gravity waves is less than 0.01, right, from large-scale structure. We're going to assume the Copernican principle, that we don't occupy some preferred location in the universe. You'll never get any constraint if, happens to be a huge source in the next room. I'm going to, since I'm looking at z less than a few, I'm going to cheat a bit and treat space as Euclidean. And I'm going to assume no extreme beaming of gravitational waves. So in fact, as we showed in the paper, and as I recall, Kip showed in his paper too, I think, even extreme beaming has a very small effect on the limit.
Wait a second, if there's a huge source in the next room, as you say, you wouldn't have a good upper limit, but you have a detection, right?
Let's see.
It wouldn't look like that it wouldn't have the same directional
Right. So
structure.
the point, I guess, one of the reasons I was to do this is that it's also to say where not to look, for example. So I want to say, okay, it's really not useful to sort of use the DSM to look every day at the pulsars because there just isn't anything there. That it's true, it could be something in the next room, but it's very unusual. I'm going to sort of discount it. That's the sentiment I'm using. But yeah, you can always get lucky. So I'm just going to tell you what it's, just a very few things get used here. It's just basically counting up the energy and assuming things are isotropically distributed. Okay? What gets used? Well, and I won't put in factors in front for this beginning of the argument. Well, the energy in any given, say, burst of gravitational wave radiation. Well, then we're going to look at the strongest one, so the nearest one, basically, for any given source. Well, it's going to be clearly go to proportional to h squared times the frequency squared times d squared times how long the signal lasts. So that's how much energy is in it, basically. Modulo factor of pi. Okay, if you look at, so that gives you relates delta E to h. If you say, okay, a lot of bursts make a lot of omega gravity waves, right? And so you can't have too many, or they can't be too strong, or you make omega gravity waves greater than 0.01. So the relation is, so this omega gravity waves is the fraction of energy density in gravity waves. So omega gravity times the energy density today is the energy in gravitational waves. And that's saying that this is basically the sum of the energy from all the bursts. So each burst gives delta E, and dot is the number of events per volume per time. And then we're going to assume it's also roughly constant over the age of the universe for this kind of approximation. And for this approximation, it's 10 to 10 years. What's the nearest burst? Well, assume for a second that the length of the signal is less than t observed, so max of these two is t observed, then it just says the nearest one, that the volume over which you, 1 over the volume over which you have to search is proportional to the rate times the time, right? The volume space is free. And then the signal to noise of that source, well, it goes like h, signal to noise squared goes like h squared after minus 2, and then it depends how long it lasts, how long it's on. So the signal is longer than the observation time. Well, that doesn't help you at all, because you only collect signal noise during the observation time. If the signal is less than observation time, then you only collect signal during that. And then these are the definitions. Tau naught, the age of the universe, I'm taking it in 10 years, and that again is the space-time rate, number of events per volume per time. And rho naught is, roughly speaking, is the energy density of the universe today, is 0.1 divided by the age of the universe squared. Close to that. And if you just put those together, you get the signal to noise of the nearest source squared, then we put in the factors, it's 2 times 10 to the minus 4, proportional to omega gravity wave, because that's proportional to h squared, and omega gravity wave is proportional to h squared. With these different factors, it goes like 1 over the noise in each pulsar. M is the number of pulsars, so noise squared scales with the number. P P is the observing cadence, say like once per week, so P times T observed is the number of times you observe each pulsar. And then it's divided by F to the fourth and the age of the universe cubed. Part of that's going into making energy density with it. And then times the distance to the nearest one. So now, the interesting thing is the most favorable case for signal to noise near is actually one with D near as large as possible. This is actually Kip's paper, Zimmerman and Thorne. So you might think that it's good to have the source close to you, but actually you get the strongest source if there's one really big one, and then if there's one really big one that is contributing, at the right at the edge of the universe, that's going off there once every T observed. So the strongest source comes off is actually as if you have one going off say every 3 years, and it's at at z equals 2 or 3, right? And it's all coming from that one.
It's Olber's paradox saying that your gas is one object.
I hadn't thought of it that way, but I'm sure you're right. Okay, for this argument, I'm again looking at only things up to z equals few, so I'm taking d near then as tau naught to cut it off. Okay, and then you can evaluate this. And then you can scale it in a couple ways. So the max, you can scale it in terms of omega gravity waves, assuming 10 to the minus 5 or 10 to the minus 2. Let's take this one. So, and using no assumptions of what the source is, just using conservation of energy and isotropy. And allowing omega gravity to be as big as it possibly can, omega to the minus 2. And then this OBS is just so I don't have to keep writing this over and over again. It's basically fiducial numbers. It's delta T RMS over 10 to the minus 7 seconds. It's a good pulsar timing. And MP T observed over 10 to the fourth. That's 10,000 observations total, basically. This will eventually be a little larger, but not by a lot. And it said, and if you look at 10 to the minus 5 hertz, which is what we're quite interested in once a day, it said there's no way in the world you can get signal noise bigger than 0.03, right? Well, it's statistical, so maybe if someone came up to me and said, oh, I found 0.3, I would say, well, yeah, there was a 1 in 1,000 chance of that. I guess I'm not, I guess that's okay.
Because is it the T obs in your equation 5.9, that's in units of seconds? Or?
Right, so P is in units of 1 over second. It's a rate.
Oh, okay, so that's
So, yes.
So P is the
P is the rate at which you want.
That's the rate at which you observe.
The rate at which you observe.
Okay.
I'm sorry. Oh, that was a bad choice, wasn't it? Yes. The rate at which you observe. I'm sorry. Okay. So it tells you basically, you should not bother looking for pulsars or anything at 10 to the minus 5 hertz. This, I think that's a very strong conclusion. I won't. You can. I showed you what went into this derivation, just energy conservation, really calculating isotropy. You can redo the whole thing with 1 plus z's in. I won't do that at the moment. I'll just tell you the answer. If you redo it all with 1 plus z's, the right-hand side just gets ended up dividing by 1 plus z to the 1/2. So it gets somewhat worse. Okay? A lot worse than z to the 1,000. Okay? That was, so far I've been talking about, I was mostly talking about low z, though I talked a little about high z at the end. Now I talk about my constraints or my assumptions for high z. They're almost the same as for low z, but with one extra assumption. Again, I'm assuming the Copernican principle, we don't occupy any specific preferred location. Omega gravity wave for these, they say less than 10 to the minus 5. And lastly, I'm going to assume some, what I would call naive causality condition. That is to say, if you look at the source that's, say, coming from time t of z, there's some Hubble length or Hubble at that time. And I'm assuming nothing that's bursting is bigger than that. And takes more, and emits more energy than exists in that volume. So I'm assuming that at very high Z, somehow there isn't some conspiracy that all of these different Hubble volumes together are somehow radiating something out. Okay? And then it's sort of a naive condition because in quantum mechanics, I'm sure it would be possible that the states as they are somehow beaming towards one. But it's a standard kind of assumption. And I've already given you the answer for direct waves that in fact just gets worse in high Z. So now I'm going to look at the memory effect. Because the memory effect, it turns out, will be sort of the most interesting one of all, especially the high Z one. So again, I'm just going to sort of get interest going in this. Trying to review first primer on the Christodoulou memory effect. So I'm assuming that a lot of people have probably heard of it, not everyone quite exactly remembers. The point is, if you have, say, this is a gravity wave from, say, binary inspiral, you might have thought that, it just comes back asymptotically to 0 at the end, but that's not true. It will asymptote to some constant value, and that constant value is representative of the memory. How does that come about? It shouldn't be too surprising, actually, if you just look at the quadrupole formula, that Hij is 2 over the distance times the second time derivative of the quadrupole moment. And imagine the source is a bunch of masses. X Ij is sum of all the masses times x I xj. And take its second time derivative. Well, you've got a couple pieces with 2 time derivatives on the x's. But you've got another piece with this an xi dot and an xj dot. So if you have masses, say, that go out, or if you imagine an explosion, say, and it ejects mass from up the top and down the bottom, right? Over time, those masses will reach some constant velocity, right? You might think at that point the gravity waves would turn off, but they don't because of this term. That stays constant. Now that is the memory term. And then, so this would just be the quadrupole formula. A better version is this one. So this includes relativistic effects, but it's very similar. Notice it has this V, V, V. But then the masses are, it's really the energy M over 1, it's V squared. And there's another correction factor. Was it Bill Press who worked it out? Was it you? I don't remember. I remember what method, I don't remember the first one.
Well, all I did was I took Christodoulou's paper, which nobody could understand what he was saying.
No, I
translated it into this, but that formula, some more sophisticated version of that formula is due to Bill Press.
It's Press, okay. It's actually a beautiful derivation, I wondered that. And then Bill Press was, by the way, I remember using a method in Weinberg.
Kurt, this is new for me. This,
Oh, okay, good.
where you're talking about, as a simple way to think about it, there's an explosion and the mass is going out from a merger. Could I think of if the merger results in a kick and the black hole goes off in some direction, would that lead to this effect as well?
I haven't stopped. I'm going to answer that in the next slide.
Okay.
So this was just to motivate the memory effect using sources which are masses, physical masses. But the point is, and something to recognize, that first, Christodoulou in '91 showed that you get the memory effect without matter, just in pure GR. And then Kip showed very shortly thereafter that Christodoulou's result is based on just an obvious extension of an older result. If you take these masses, the two physical masses, and replace them by basically the mass of the gravitons going out, and V is now 1, then you get Christodoulou's answer, right? So it's the same thing, except you're basically using the energy of the gravity waves as the source. So it shouldn't be surprising. A useful estimate of the size of the memory effect is it's basically the amount of energy in gravity waves that's emitted divided by the distance to the source times a factor alpha that depends on how asymmetric the source is. Again, if it's spherically symmetric, alpha would be 0. But alpha is 1 basically for binaries. And then divided by square root of 6. Okay? So that's a simple estimate we'll use.
I guess for neutron stars and supernovae, which are not relevant, there's also the neutrino peaks, which should be
There's
the
lots.
same way.
That's right, that's right. I was thinking of that, but that's right, absolutely. Okay, what's the effect of the crystalline memory on pulsar-timing arrays? Well, the point is, this memory effect, which is like a step in H, is basically, and turns on fairly fast as the energy is emitted, basically is like an instantaneous or fairly quick change in the frequency. You can say it's like a glitch. Which is proportional frequency, delta nu over nu, goes like basically each memory. And so on a glitch, if you then turn it into timing residuals, is something that we'll call the linear growth of the timing residual. So it turns on at some point as the memory passes over you, stays constant, and then grows linearly in time. Okay? So you have a bunch of, so suddenly a bunch of timing residuals turn on in pulsars. Of course, in any single pulsar, you would say it's just a glitch. However, the point is, within the errors of how well you can determine them, all these pulsars would be glitching at the same time, and they'd all be glitching with consistent amplitudes based on where they are in the sky. So,
Would tempo fit it out?
boy, I don't think so. Oh no, we know that it won't because somebody's looked at it. In fact,
I mean, does tempo allow for glitches in the pulsar frequency?
Oh, you could, but the nice thing is these millisecond pulsars that are used for gravitational wave detection, we've only seen 1 or 2 glitches ever in that. And that's one of the reasons why we take them, because they're so boring and stable.
in fact, Rutger and your 11 has gone to the trouble of saying, okay, if you have a memory turn on, what's the signal to noise after you do these fittings, after you fit for dot for new and dot and things, because that does decrease the signal noise somewhat. And they came up with this formula, which I just been stealing, that the typical signal noise from the memory effect is, again, h mem times t observed, that's roughly the timing residual, times the factor 1/20th, divided, of course, by the usual error in the pulsar signal, and the usual scalings with number of pulsars, and like that. So there's this 1/20th in front, so we'll use that. See, so now I'm going to skip right to how redshift affects H memory. Okay, you might have thought, okay, now I'll do a calculation about local universe, but the far distant universe is actually more interesting. So I'm going to skip right to the high Z universe. So again, just for the last transparency, HMM is the amplitude of the memory H, so that's alpha over square root of 6 times delta E over D. The standard translation for basically all expressions for gravitational radiation emitted is the mass is basically get redshifted by 1 plus E, and the distance goes to the luminosity distance. If you just use that standard translation, well, delta E is like a mass. So then the H memory effect was like simply alpha over square root of 6 times the M is the locally measured M, the E is the local, how much energy is emitted in the local frame. There's 1 plus E over the luminosity distance. And you might have worried that, well, okay, maybe this formula works all the time, but not for this case. But I have checked for a few special cases, so I'm confident I could show you special cases that this, in fact, is the right answer. For very high Z, also the luminosity distance goes to a constant, the age of the universe, times 1 plus E, 3, right? So the memory effect, HMM, so DL is proportional to 1 plus E, which cancels that 1 plus E. It's just alpha over 3 root 6 times how much energy was emitted locally divided by tau naught. And notice it's independent of Z. That's the amazing thing, sort of. So, if the universe dumps a lot of energy into gravity early on, that memory effect, the energy redshifts away. But the memory effect doesn't care. It just stays the same. Okay? So unlike energy, HMM does not redshift away. And so memory effect is actually a particularly good term because the universe remembers them. It remembers the gravitational wave bursts despite the redshift.
I think the point is right, just the fact that the memory residual is growing with time, which exactly cancels the redshift.
Um,
Right, in other words, the burst
Yeah.
that, if you would put the burst at a higher amplitude, there's a smaller energy flux coming by the Earth by 1 plus V with the amplitude and the residual was grown by
Right,
the
I
same
think that's
factor.
it.
So
That's probably a good way of looking at it.
There's another way, we know that during inflation, the gravitational waves freeze at constant h,
Oh.
because the time scale for evolution of the universe is short compared to the gravity wave period. It's the same thing. They're frozen.
Of course, yeah, that's like, I like that, I haven't thought of it.
So, here delta E local is the energy that is injected in a given jet of,
Yeah, whatever it was. And here, I'm assuming that anything that I think is gravitational wave, not neutrinos or something like that. You could generalize it, but for the rest of the derivation, I'll assume it's something that emits lots of gravity. Some unknown, yet to be discovered thing emits lots of gravity waves that have been redshifted away by now. However, and maybe not be in any band that's of interest, but their memory effect is still detectable by pulsar-timing. Okay, what's the maximum signal to noise for a memory effect? I'll just tell you again what goes in and what comes out. So they're all standard things. So the energy today is the energy then redshifted down by 1 plus Z. I'm going to define B as the number of bursts per Hubble volume. You know, there's something's happening at some Z, and each Hubble volume is producing some number of bursts. And I'm assuming it's not much less than 1. I'm assuming that they're not, that a bunch of Hubble volumes aren't contributing together to make one big burst. The number of Hubble volumes then within our Hubble volume today is just T0 over T cubed. And then energetics says that basically the density in a gravity wave today is related to how much energy today is from each of the bursts, and these are all the bursts. This is the number of bursts. So each Hubble volume produces B bursts, and this is the number of Hubble volumes. So this is just adding up. I'm assuming that the observed rate of events now, just so we can see them, the observed rate now times the observation time, like 3 years, has to be at least 1. That's a constraint. I don't want it to be every 1,000 years, which also is a constraint on B and these other factors. Again, we just have the formula, I'm just copying over the formula from H memory and copying over the formula from SNR. And now you put those together, here's what comes out. So you can get a rather large number. So the maximum signal to noise from the memory effect can be 270 times, say, alpha, which is again order 1, times this factor 1 plus Z over 10 to the 7. Even at 10 to the 7 Z, you get a very large effect. This is even for very tiny omega gravity waves, at 10 to the minus 10. If the amount of gravity waves produced by this, whatever it was, is 10 to the minus 10 today, the memory effect is great. It was produced at Z equals 10 to the 7. And I'm assuming that we've observed for 3 years, and look at these standard numbers about how well the pulsars are timed and how often we time them. And so this is what I think the most interesting result of the paper, that you can get a very, very large result. Okay, you can ask at high Z if the energy. Another way of saying it is, it's just that we're not. You can also put it the other way. We're just not very well constrained. This is to say, something that injects lots of energy in the early universe is redshifted away to something like negligible. So we don't have much constraints on it. But even if it's small, we still get a large signal noise. I showed you that what goes into the high Z case. If I just did it at the local universe, I would get the very same thing basically, but a factor. This is a factor of basically 1 plus Z larger, right? So at Z equals 1, it's 10 to the 7th smaller, right? Which is to say negligible, right? So this effect is very interesting for sources that inject energy in the very early universe. Some crazy thing. Okay, so I'm at the end. My summary conclusions. One, was that, just we did that check, just reminding you that that there could, if there were high frequency gravity waves, 10 to the minus 6, 10 to the minus 5, can't be, but if there were, that wouldn't be fitted out by tempo. That the direct detection of gravity waves at 10 to the minus 5 would require either a violation of very fundamental assumptions, like isotropy or energy conservation, or being really lucky, like being in the next room. And the last one is that the early universe dumped a lot of energy into gravity waves. The most detectable signature of that could well be the memory effect on PTA timing residuals, and it would detect things that nothing else would detect. And so we're recommending that in PTA data analysis efforts, they look for this as part of the discovery space. They look for correlated memory signals as at least a wide open area for something that might have happened in the early universe. Thank you.
So this last bullet point is pretty interesting, so it's an interesting punchline to your talk. So what does that mean to look for, I mean, what do you do differently in your search to look for memory residuals rather than looking for stochastic background? What is the signature of this memory residual?
Well, stochastic background, again, would be assuming that all the signatures would look quite different, actually. So A, you would have a very definite pattern, right? It's a glitch at one time, as opposed to some random thing that's correlated. It would also be correlated, but in a very definite pattern. And also, so the Helling-Downs curve I showed is based on assuming that we had an isotropic distribution of sources on the sky, where this is one guy. It will just fully to correlated residuals, but based on one initial source position.
I see, so this glitch is really, you're talking isolated events, not some integrated signal.
It's an isolated event, but in the gravity wave memory, which leads to a growing signal in the pulsar. The time residual grows annually.
I see. So that is basically.
That's kind of the nice thing about this is once it turns on, the signal just grows and grows and grows.
But it should have a quadrupole pattern
It does.
on the Earth, which will grow as opposed to the.
That's right.
That's
It should have a very simple pattern, a quadrupole.
So can I ask the beaming, I guess, the question of the strings, there's sort of been this long controversy of whether it's the stochastic background or the rare cusps that are aimed directly at you, which are sort of beamed, I guess. Does that, how does the beaming come into this?
Right, so.
The strings are obviously going to be extremely beamed.
Right. So, this was in Kip's paper, I think. So if things are beamed, right? So on the one hand, a lot of energy is coming directly at you. On the other hand, for total energy in the universe, I mean, mostly they miss you, right? So the nearest one is farther away. And it turns out those factors almost, but not quite cancel. So if the beaming fraction is F, F is say for like 1 over a few hundred, say for gamma ray bursts, right? It only it does enhance the signal actually, but by F to the minus 1/6 power. So unless it's beamed by 10 to the 12 or something, it's not going to make if you work it out. And that's for signals. I don't think I can quickly show you, but it works out pretty easily. And that's for signals in the local universe, d less than 1 or so. If it turns out by kind of an accident, coincidence of cancellation, if you look at beam sources at high Z, there's no effect at all. They completely cancel. So you get the same limit. One other thing, as long as we're mentioning things, and this is a main paper. In terms of other things I could have done differently, I said stochastic, I'm assuming the sources are isotropic in the universe. Well, we don't live in that exactly completely isotropic place. We're in a galaxy, right, with other galaxies nearby. If you imagined instead that these sources were isotropic, but only located in clusters of galaxies, And of course, you get some enhancement because you're closer to them. And all the limits just go up, but just by a factor of 10. So it's not a huge effect. Any questions?
So have you thought of any sources at 10 to the minus 5
No.
hertz?
No, I don't, but that's a great number. How wonderful it will be, how much we'll learn. No. I think it's worth looking. Okay?